by 4, and you get 7.5 centimeters. And it's not in the vacuum, but it's the speed of light or electromagnetic waves in the insulator that is used to insulate various parts of the circuits. So on a chip, this is most likely silicon dioxide. And the speed there decreases to about 200 millimeters per nanosecond. So this means you have the signal travels only 5 centimeters during one clock cycle. And this is about the scale of the chip. So probably there is some link in there. Still, at the increasing computing power, there is another thing that arises, and we will interact with that, although it's not so explicitly seen in the programming, is that we have an overlapping of instructions, of CPU instructions. So you don't have even the thing that each CPU clock means one instruction. Depending on some things, the CPU will be able to execute several instructions in the same, or the number of instructions executed in a certain length of time may be even greater than the number of CPU cycles in that time. So the average number of instructions per CPU cycle may be quite large. Because although, on the other hand, CPU instruction takes more than one CPU cycle, typically. And how is it done? Because you have some parallelism at the level of the CPU itself. The CPU is able to execute several instructions in parallel. And there are lots of hardware optimizations in order to do that. And to detect which instructions can be executed in parallel, because of course, if one instruction uses as input the output of another instruction, then it cannot be executed before that or fully in parallel with that. And here again, the beginning is quite old. At least the Intel 8080 or 8080, which was at its time was a very well-known and used a lot microprocessor in the end of the 1970s, beginning of the 1980s. It already had some overlapping between the instructions. So the next instruction was loading during the current instruction. If the current instruction, the only thing that it did was an arithmetic operation between registers with no memory access, then the circuits involved in loading the next instruction were free during that time. Loading the next instruction is not influenced by the current instruction unless the current instruction is a jump. So it was perfectly possible to overlap those instructions. And this is a kind of parallelism between them and made that the sum of the numbers of the CPU cycles of the instructions is larger than the actual number of CPU cycles consumed for executing the program. So this would be the second reason why using parallel programming. Now, the next reason, and we are going now into the distributed system, we have computers that are local to some place, and they have data that is local to some, let's say, an institution or the local chapter of an institution or something like that. And you want to be able to access data that is elsewhere because it's local and it's more involved in another place. Now, of course, one way of dealing with that is to have a centralized spot where to put all the data for all the systems. But another, and that's kind of becoming popular with cloud computing, although there are again pluses and minuses. But another possibility is that, and even with cloud computing, the things become a bit cloudy in this direction. But otherwise, you have, let's say, a local database that, and everything that is around that contains your data, and you may have access to some remote institution or remote location where is some data that you don't use as often, but you use from time to time and in integration with what you do locally. And yet another thing, redundancy. That's a lot to talk about redundancy. But the basic is clear. You may have multiple devices that do the same thing or are capable at least of doing the same thing, so that if one of them fails, the others or one of the others can take over the task. So let's say you have two computers for acting as a web server or whatever kind of server. One of them is actively serving requests, and the other is kept up to date to take over if the first one fails. Or maybe both of them are serving requests, and if one of them fails, then, the capacity decreases a bit, but the system continues to go. By the way, the internet itself is a very good example of this redundancy, and routing protocols are designed so that if whatever node of the internet fails, the routing goes around that node, and the packages that are lost because they were on the failed node, they are somehow retransmitted or so on. Now, redundancy is not an easy topic, and especially when talking about computers, because you have to understand well when you embark on this redundancy stuff. You have to understand very well what are the failure modes that you go to protect against. And some of the failures are independent. Some of the failures will be correlated. If the failure is because you have a hard drive that for some reason, let's say, wears out and crashes, then it's an independent fault. And if you have several hard drives, the probability that two of them fail at the same time is the product of the probability of each one of them to fail. They fail completely independently. Also, same reasoning would probably apply when talking about fires or earthquakes with data centers that are far away from one another. But on the other end, programming bugs are not independent. If you have two servers that run the same software and the software has a bug, then both systems have the same bug, and in front of the same conditions, they will likely fail at the same time and in the same way. And here, a classical example, we won't discuss much about such things anyway, but a classical example was the Ariane 5 rocket that failed spectacularly on its first flight. Fortunately, it was only about money that were lost. And the reason was that the inertial guiding system of the rocket had a computer bug, actually had a piece of code that was inherited from the previous model, from Ariane 4. It wasn't actually used in Ariane 5, but was incompatible with the data, and this meant that at some point it ran into an arithmetic overflow. And that was throwing an exception that was not handled and led to disabling the inertial guiding system. And both systems ran the same software with the same bug and failed at the same moment, more or less. And without guiding, the rocket was destroyed. So the take-home message is that redundancy is quite hard to achieve, especially when we are talking about programming bugs as opposed to pure hardware failure. Even with hardware failure, there are lots of examples where they are correlated instead of being independent. And well, think about what's the probability of having a 4-engine aircraft having a quadruple engine failure. In other words, remaining with no functional engine. Well, it depends. If it's a problem with a fan blade, then the probability is quite low. If the problem is that you fly into a volcanic ash cloud, then, well, the failures are not independent. There was a famous example of that as well. Look for British Airways Flight 009 for details. Anyway, back to our thing. Why not embarking into the direction of concurrent, parallel, and distributed computing? So the first thing, and we don't have to talk much about that, it's more complex, it's harder, it's easier to have bugs, it's harder to understand, harder to modify, harder to do anything. And for that reason, if you don't have a good reason to do concurrent or parallel programming, don't do that. If you have a piece of code that is not so time-consuming, so CPU-consuming that you have to parallelize it, a good enough computer will run it acceptably fast, then don't bother to parallelize it. Simply have it working serially, and that's it. Now, you have some issues that are specific to concurrency. And you have race conditions, deadlocks, live locks, even. So race conditions. Race conditions means you have some changes that happen on different threads, and each thread actually assumes that something is not changing between some operations it's doing, and actually there is a possibility to have those things changed. So here on the next lecture you have an example. And by the way, here is an illustrating joke as well. I have to redo the drawing because at some processing, this equal sign was transformed into a minus sign. It wasn't rendered properly. So let's say we are at a supermarket and we want to compute how much money does the supermarket have. So each cell will add some amount to that value. You have a global variable that holds the money of the supermarket, and each operation adds the value corresponding to the cell. So we have one operation that adds 10 money units to the initial 50 and outputs a 60 that gets written into the variable. And you have another thread that adds 25. And unfortunately, it sees the original value, it adds 25, it writes the 75, that is the result, and it overwrites the 60 here. So what is the problem here, and what we need to solve? The problem is that there is an assumption when you do this operation in isolation, namely that, well, this is the value that the supermarket has in the count. And from here to here, nobody uses this value, especially nobody modifies the value. So I do my job, I write the result, and anybody else that has to do with this global value either does it before I read the value here or after I write the result here, but not in between. And this assumption is violated here by having the second thread reading the value here. Actually, it's with respect to this thread that the assumption is violated, because this thread assumes that nobody writes the value here, and here it is the writing. Now, this is a very simple example of this, but you have to always ask yourselves, what are the assumptions about things that don't change during the operation that I'm doing? And there are a lot of things, and well, we have to take care about. And actually, it's very hard to analyze in a way to be sure that there's nothing that is still left there. Then we have the deadlocks. When we try to solve the race conditions, what we do, one thing that we can do is to put mutexes. To put a thread, wait, in a more general case, to put a thread, wait until some other thread performs an operation. And it's quite easy to make a mistake where it is possible, generally not sure, but there is a slight possibility that you end up with a task or thread A to wait for a task B to advance, and B waits for task A to advance. and they are both blocked in this case because none of them can advance until the other one does something. A related problem is what's called a live lock, where we don't have a wait with doing nothing, but we actively do some operations, but we end up over and over in the same configuration of tasks. So we have a deadlock, but without task being stopped, but rather by tasks doing over and over the same things. Now, another thing that we have, it's not probably directly a problem, but it aggravates others, is that the behavior of a concurrent system is usually non-deterministic. Because, let's go back to this picture, what exactly will happen in a system like this depends on the order in which various operations are scheduled by the operating system. And we have no control over that. So several runs of the same program may lead to different results. And that may be problematic in two cases. One of them, if you have a bug, then it's very possible that it's hard to track the bug because the bug occurs only for some of the sequences of events. And anyway, the manifestation of the bug is different each time. You don't get the same result, the same buggy result. Sometimes you get one result, sometimes you get another result. Let's say both of them are buggy, but being different, it means that each time you run the program, you have different data, so it's more work to understand what is wrong if at each run you have a different thing. So even if you don't have really race conditions, the mere fact that the output depends on something that's unpredictable, on something random, makes it more difficult to understand what's happening. The second thing is that in some cases you could want to have the same output for a given input. Say because it's not a lot to compute and it's easier to do the same computation in separate places and be sure that you get the same result than to compute the thing in one place and then distribute it. Let's say you have a game that runs in the network, and it may be easier to compute in various places to simulate what's happening than to compute in a single place and distribute to all the players. It's less lag in the game by doing so. But then you want the computation to be completely predictable. So to get the same result on all the places where you do the computation. And if the result depends on some ordering of the tasks, you fail that. Let me give you another example. Maybe some of you will use LaTeX in order to write your bachelor thesis. And a detail regarding the implementation of the TeX engine of the LaTeX is concerned with computing where to put each letter on the page. And there are some computations in order to get the optimal spacing between the words in order to fill the rows and so on. And the author of the TeX system, Donald Knuth, wrote somewhere that he used integer arithmetic instead of floating point arithmetic in order to make it predictable in such a way that if you have the source for a TeX document and you run that on different system, you get exactly the same breaking into rows and into pages, so the same output document, the same layout of the document. And that's very important if you send a paper and want to only send the source and be sure that everyone sees the same thing, or that if you run several times, you have the same layout. And he used integer instead of floating point because at that time the floating point was not standardized as it is today. And so different architectures were implementing differently the floating point operations, and he couldn't implement the operations in a predictable way. With integers, it is possible. So he went to express everything as an integer number of some very small size in order to achieve some determinism. And another thing that will mess up with our minds when going to distributed systems is that we don't have a global state. With even a multi-threaded program that runs locally on a single machine, you do have a state of the program. You can, let's say, take a snapshot of the memory and of the registers of each of the thread and to say, well, this is the state of the system. But with a distributed system, it's practically impossible, and even theoretically, you have some physical limits, see the theory of relativity, in defining what would be a state at a certain moment of a system that has one computer here and one a few thousand kilometers away. So if you have a distributed system, then each part knows its local state, but knows only about messages exchanged with partners, with the other nodes. And the order of the events may be unknown. So it's hard to define what the order of events is. Now, of course, if you have clocks, you can say that I timestamp everything. We will see that it's not that easy, because what happens if two events occur at the same time, or the time between them is smaller than the uncertainty about the local clock, because you won't be able to perfectly synchronize the clocks. And what happens if two events in different places are so close to one another in time that the time difference is smaller than the clock errors, or even the resolution of the clock. So those would be the problems that we will deal with, and we will talk about how to solve, what are the available solutions, and so on. And now a bit of classifications of the systems. I'll go very shortly about that. Flynn taxonomy regarding the parallelism. You may have single flow of instructions or multiple flow of instructions, and a single processing of the data or multiple processing of the data. So a single CPU is this single instruction, single data. A classical multi-core CPU is multiple instruction, multiple data, because each of the cores has a flow of instructions and has an arithmetic unit that processes the data. You also have, those are called vectorial machines. Single instruction, multiple data means you have a single flow of instructions, but you process of data instead of a single variable. So think about vector or matrix addition, multiplication, and so on. It's not actually used quite a lot. Now, it depends a little bit because the GPUs, the graphical processing units, in a way, they behave as single instruction, multiple data, in the sense that at least they are optimized to do some vector operations, even if maybe not the full vector is processed at the same time. And multiple instruction, single data is put only for because you have a place in the table, but it's not something of practical use. Unless you think of a system where you have some cross-checking, let's say some redundancy and cross-checking as being such a thing. Now, more to the point will be this classification. Do we have a shared memory, or we communicate only via messages? And the difference is not as clear-cut as here, but let's go a bit into the classification. So this is the idea of a multi-core CPU. So we have several identical cores or processors, and we have a main memory that is shared between them. So all of them can access on the same footing the main memory. We will see shortly that this model is an oversimplification, but it's a good starting point. You can have asymmetrical multiprocessing, which is like this one, but some processors have different capabilities. So some are more special than others. And you can have non-uniform memory access, where you have both local memory and main memory. So not all the memory parts are equal. So it's a bit like you have multiple computers, multiple independent computers with the access of with also accessing a shared memory. The second approach is to communicate via message passing. So this means each processor has its memory and has no access to the memory of the other processors, but each processor can send and receive messages from the others. The main image here would be several independent computers that are connected in a network, in the internet or in a local network or whatever. And here again, you have cluster computing and grid computing, where the term cluster is used to design is used when you have multiple computers that are connected, but they form a special device. So the connection between them is specially designed to be very quick. Maybe it's a special topology. Let's say a star, a ring, a hypercube. A hypercube would be a very good compromise between the complexity of the networking and the accessibility between the components. And the computers that are packed together are generally of the same type. Identical processors, identical memories, amount of memories, and so on. So they are special devices that have multiple computers, let's say, interconnected. And grid computing means essentially you have multiple PCs or whatever computers. As I said here, maybe of different types and characteristics. Maybe some of them are ARM processors, some of them have Intel compatible processors, maybe different amount of memory and so on, and linked together in a network with probably nothing special. So Ethernet on local networks or whatever network technology we have. And then it means you have probably some middleware that allows to write a bit easier program that treats the set of computers as a single system. We'll discuss a little bit in the second part of the lecture, so mid-semester or so, about the MPI framework, and you can consider a program that runs on MPI as being on a grid computing in the sense of this definition. Okay, so that would be the basics, an overview of what we are going to talk about and what's the terminology and so on. And this is put on the first page here. Now, for the remaining of the lecture today, I will start digging into some hardware issues regarding the CPU. And we encountered this and influences a lot, I'll show you next time, the performance of the programs. So I talked a little bit, just a bit earlier, about symmetric multiprocessing. And I said here that we have identical processors that access the same main memory. And this is the model that we have in a program with multiple threads, and each thread can access the same variables as the other thread. So the global variables are the same, the heap is the same. So if one thread somehow passes a pointer to another thread, the other thread can access the same variable. It's a model that's easy to understand, but unfortunately, it's not that good to implement directly. So the theory would be that you have a simplified version of this picture where you have only the first layer and the last one. So you have the CPUs, and all of them communicate with the main memory. Now, why this is not so easy? What's the problem? What are the problems here? And the main problem is, and it's quite independent of concurrency and parallelism and stuff, the problem is that the main memory is slow. And larger the memory, slower it is. Now, slow in the sense of the response time, because always when talking about communication speed, we have to have in mind that there are two very different parameters, the response time and the throughput. And the throughput is good or can be very high for the main memory. It's not a problem. You can read a lot of bits in a second. But what's of interest is the time from the moment we know that we need some data at some address until we get the data. Because we are very constrained in what we can do during this time, because we can do only unrelated operations. If I know at some point that I need that my data is at this address and I need the data for further computing things, then I cannot do much until I get the result. Consider something like this. I have an instruction like A equals B of I plus, let's say, B of J. Something like this. And now the machine will have to compute the address corresponding to this index. So take the address of B plus I times the size of the element, and then go to the memory and extract B of I. And the addition cannot be performed until the processor has this value. What the processor can do is to try to compute the address corresponding to B of J and to ask the memory for B of J. But until the CPU has both results, it cannot go on and perform the addition. Maybe we can find something else in the program that is completely independent of this statement, but apart from that, there's nothing we can do. And the time needed for accessing the main memory is in the order of at least tens or maybe around 100 of nanoseconds. Now, consider this, tens of nanoseconds is a lot. Is, let's say, around 100 or maybe several hundred CPU clocks. So there are a lot of things that can be done during the response time of the main memory. So then the idea is you cannot speed up the main memory without increasing a lot the cost of it. And even so, you have some limits. So what you do is to put, let's ignore for the moment those two layers. You put a smaller memory that is faster. Because somehow a large memory is, because of physical constraints, it's slower in the response time. If you have a lot of memory cells, you have a lot of circuits that must stabilize between the time you ask for a memory cell and until you get the result. Now, you can ask for a lot of memory cells and get them at the same time. That's why I said that the throughput is large. But the response time, as I said, is slow. So what you can do is put a memory that is smaller but faster. And there will be two things happening here. First of all, you put in this smaller memory the variables that are accessed more often. So let's go back to this example. The variable I, for instance, and J can be kept into registers or maybe in this cache memory, this smaller memory. B, if it is a small vector that is used a lot, it again can sit in the cache. And you keep in the main memory only the variables that are used more rarely compared to the other ones. And this way you can optimize the things. So you put a faster and smaller memory where you put the objects that are accessed more often. Now, if you do so, theoretically, you can have two strategies. Either the programmer declares, I want variable I to sit in the fast memory and variable J to sit in the slow memory. And this complicates the work of the programmer with theoretically potentially very high gains. Practically, if the programmer is not that smart or doesn't have enough time to optimize everything, it may be worse. Or you put the CPU to optimize the things, to choose where to put each variable. And this is what we are doing typically. So the cache memory means you have this memory that is smaller and faster. And there is a simple strategy of deciding what sits where. Namely, everything sits in the main memory. When you need something, you bring it into the cache, and it sits there until the cache fills up. And when it fills up, when you need to bring something in the cache, you remove the variable that was least used in recent time. So least recently used is the main, or the basic of the strategy of what to cache and what to send to the main memory. And it's implemented in hardware so that this in itself is fast. And well, that's how the hardware works. What's of interest for us, even when not digging into parallelism, is, so first, that if you have small enough data, it will sit in the cache. Second, the communication between the main memory and the cache is done on the basis of large chunks of consecutive memory cells. Those are called cache lines. And effectively, it's not a single byte of the memory that can sit in the cache or not, but it's the cache line it belongs to. And the cache line is typically 64 bytes. Be careful, 64 bytes, not bits. So 64 bytes, it's quite a lot. And a full cache line is typically transferred between the main RAM and the cache. What it means for us. It means that if I have a matrix and I'm doing something like this for I equals 0, I less than n plus plus I, or j equals 0, j less than n, and then, okay, let it be the same, n plus plus j. And here, I'm doing something. I have a matrix A, and I'm doing something with A of I and of j. Let's say I'm doing some s plus equals this value. So consider this versus I'm doing exactly the same, but I interchange I and j. So the outer loop goes on the second index, and the inner loop goes on the first index. If you run those two programs, those two code snippets, chances are the first one is way quicker than the second one. You can even get it running more than 4 or 5 times faster. So it's not something negligible. Now, why do you think we have that?
Because the first loop parses the matrix line by line, so array by array, and since an array is a contiguous segment of memory, we will have chunks of that array loaded in the cache, so it will be faster to parse. On the second loop, it parses it column by column, so it has to switch array at every iteration of the inner loop, and so it also has to load different arrays at every iteration of the inner loop.
Perfect. So, of course, this assumes that the representation of the array is row by row. So this means by incrementing j, I go to the element at the next address. By incrementing I go a lot farther away. And this means that this essentially parses consecutive cells in the memory, while this one jumps. It jumps. So let's say this is the memory. One of them takes cells one by one, and at each beginning of a cache line, it has a cache miss. It triggers loading the full cache line in the cache, and then subsequent accesses will be in the cache line that was just loaded. While the other way is I read this element, then this one, and then when I increment the index in the outer loop, I go with the second element here, then the second element here, then the second element here, and so on. And it is possible that by the time I reach this second element here, the cache line containing it is already replaced by something else because I haven't accessed, by that time, I haven't accessed that for quite a long time. Now, everything here has to do with the size of the array. So if the size is small, then chances are those two will run in the same amount of time, more or less. The size of the cache line, and so on. Another place where you run into these issues is what's called structure of arrays or arrays of structures. So for instance, you have to represent several points for a graphical application. You can go with struct point with int x and int y, and then have a points of whatever number of points. So this would be array of structures versus structure of arrays like this, with int x of something and int y of something. And depending on the most used case for the in the operations you have, this one may be better or that one may be better. If typically you do some processing on both coordinates of a point, then this one would be better. If you have some processing involving only the x's and then only the y's, then of course this one will be better. Now, the second thing that I will just start now and then we finish for today is that typically we have we have several CPUs, and now the question is, does each CPU has its own cache, or do they share the cache? Now, if they share the cache, then the access to the cache is slower because you have to either provide separate channels for each CPU, which is very expensive, it's very hard to implement, or effectively each CPU, the CPU access to the memory is serialized, and you kill the parallelism this way. You put a bottleneck on accessing the cache. So typically the solution goes into the direction depicted here. So you have, first of all, you have several layers of cache, with lower numbered layers being smaller memory and faster in the sense of the response time. The response time here is much smaller than the response time here. And the first layers of cache are per CPU, while the last one is typically shared between the CPUs. But then you run into another problem. What happens if two CPUs want to access the same variable? Then, if this CPU wants to access a variable, it will be loaded eventually into the level 1 cache of this CPU. But now, if this CPU wants the same variable, it needs to somehow realize that the variable is in the cache here. Maybe it has been modified here, so the value in the main memory is not up to date. So when it needs that variable, either it gets it from the cache here, or somehow it transmits a message to the cache here that it wants the variable. So the cache here will push any change back at least to the shared cache level, and then we load here from the shared cache. Anyway, it's more expensive if we have to do that. So if the same variable is modified by several CPUs on different threads that run at the same time, it will play ping pong between the caches, and it will be quite expensive as far as the time is concerned. And the same will happen even on different variables if they are close enough to one another to share the same cache line. This depends a bit on the architecture here. So on different CPUs, you will get different results. So here is an example of this. The good way of using this picture is if you have only read access to shared variables, because if the CPUs need only to read the data, then it can be had as copies in each of the caches. So if this CPU needs to read a variable, it gets loaded here. If this CPU needs to read the same variable, it gets into this cache as well. And it's possible to have copies of the same variable in both caches, as long as they are clean. Nobody modifies them. And this is the way to go into the parallel direction while avoiding the concurrency problems. And we will see, and we'll discuss next time about that this effectively breaks the locality, and we will have to run, at least at some level, into the full problem of a lack of a global state, because it's not so easy to deal with that. But that will be next time. So that would be for today. Please ask any remaining questions, and I remind you to please interrupt me and ask any questions that you might have.